Okay, good morning, everybody. All right, so picking up from where we left off in the last class, we're talking about static. So we just finished talking about static fields, static final fields. We're now talking about static methods. So we've seen static methods already in the course, right? So everything we did in the first few weeks of the course involves static methods. So just recall that a static method is a per class member, right? So in other words, static methods belong to the class. You don't associate a static method with individual objects. So you don't need a reference to call the method. Instead, what you use is the name of the class. Static methods are sometimes called class methods in Java, right? So the emphasis on class, so that because the methods are associated with the class, not objects. Oops. This is an example of a little static method. Oh, hang on, something's missing here. Oh no, it's fine. So here's a static method in the domino class. So we have a method here that checks, is that value? Is that a valid domino value, right? So is it between 0 and 6 in this case, right? And that's all it does. There's no reason for this method to be a non-static method, right? So in other words, you don't need an object to call this method. So it doesn't make sense to make this method a non-static method, right? This method only needs access to the static fields of the class, right? And it doesn't need access to any value belonging to a domino, belonging to a particular domino object. Therefore, it makes sense to make it a static method. When you use a static method, you always use the name of the class. Well, you should always use the name of the class to call the method, right? So here we use the name domino to call the method. Now, unfortunately in Java, the language allows you to call the method with a reference, right? So notice that it's considered bad form though. So for example, I can make a domino object, right? And then call the method isValueOK using that object, even though the method is static. Right? Now the reason you shouldn't do this is because if another Java programmer reads your code, and if they're not familiar with the domino class, they're going to look at their code and say, well, isValueOK is a non-static method because you used an object reference to call the method. Again, notice that it doesn't make any sense to call this method with a domino object, right? Or, sorry, it's not that it doesn't make any sense, it's that it's unnecessary to call this method, this method with the object D. Right? The method doesn't use the fields of D, right? So it doesn't use the 3 or the 4 inside this method. So it doesn't make, so it's unnecessary to require an object to call this method. Oops, sorry. All right, so utility classes. So we've actually seen utility classes already. So your assignment 1 and 2, the life2 class, is a utility class, right? It's a class where everything is static. So remember what a class is? So a class is in Java, it represents a type, right? So it's a user-defined type. And that means it's really a model of a thing or a concept in Java, right? Because that's what classes do. They model types. Also remember that a class is used as a blueprint to make objects, right? So when you create a new object, you take the class and you can think of it as making a copy of the class and using that as your template for an object. So occasionally, so very occasionally, it's useful to make a class where you're never making objects with the class, right? It is uncommon, but sometimes it is useful, right? So these types of classes are called utility classes, right? In these classes, you'll see, if you look at their documentation, you'll see no constructors, and you won't see any methods that return objects of that type. So in utility classes, all features are marked as being static. Right? In other words, you use the name of the class to access all the features, right? The fields and the methods. So examples of utility classes in the Java standard library are things like math, arrays, and collections. Right? So why do we make utility classes if they're so uncommon? Right? So the reason you make them is because they're useful sometimes when you want to group together a bunch of fields and methods that are related to one another, where you never have to make an object. Right? So for example, Java lang math, all it does is group together some mathematical constants and some functions, and that's it. right? You don't need a math object to compute the cosine or the sine of something. Collections groups together methods that operate on Java collections, so things like sets and lists. Right? So I don't need a collection object to sort a list. Right? Utility classes are never used to make objects. Right? So all you're using the utility class for is to call methods and to use some fields that belong to the class. So when you use a utility class, the only thing that takes up any memory is the class itself. Right? So there's no objects made using the class. So for example, when you use the math class to compute the cosine and the sine of an angle, right, you never make a math object. If you were to look at what's happening in memory, the math class is in memory somewhere. Right? Its fields pi and e, they're also in memory. Right? They belong to the class. When you use the math class, though, there's no math object. Right? You just use the features of the class. Right? So you can call cosine or sine, you can use pi or e, right? But you don't have to make a math object to do so. Okay, so let's create an example of a utility class. So this is a very simple class. It's got one field and one method. Right? Utility classes are really easy to make. Everything's static. So I want to make a utility class that helps you calculate Einstein's mass energy equivalence formula. Right? So E equals mc squared. M is your mass in kilograms. C is your speed of light in meters per second. And E is the amount of energy in joules. So to make the class, it's the same as making any other class. So you make a class, right? You give it a name. So in this case, I'm calling it relativity. Right? Now you add whatever fields you deem are necessary. Right? Everything's going to be static. So in this class, the only field that makes sense is probably the speed of light, right? C. So I'm going to make that a public static final constant. Right? Because it's a constant, I can capitalize the name of the field, so that's fine. It's going to be written in all caps if there are more letters. Right? And then you give it a value. Now you add your method. Right? So the method just computes E equals mc squared. So I'm going to call the method mass energy. Right? It takes in the amount of mass, and it returns a double, which is equal to the equivalent amount of energy. So if you could convert all that mass into energy, the value you would get is equal to E equals mc squared. Right? The calculation's simple, right? It's just the mass times c squared, and that's it. That's it, you're almost done. There's just one more thing to add to this class. If you wanted to use the relativity class somewhere else, right? So some other class, called 1 gram in this case, right? To use the class, you just use the name of the class, right? So it's just relativity.massenergy or relativity.c if you wanted to use the field c. So this main method computes the amount of energy equivalent to 1 gram of mass, right? And if you print out the value, you end up with roughly 9 times 10 to the 13 joules. Right? So 9 times 10 to the 13 is a large number. So that's indicating to you that if you could convert 1 gram of mass into energy, you would end up with a lot of energy, which is one of the reasons why nuclear reactors are so useful. That's roughly the amount of energy equal to the atomic bomb that was dropped on Hiroshima. Okay, so we're almost done, right? Utility class, everything's static. There's just one problem with our class. Right? So we don't have a constructor. However, you can write that, and that will work just fine. So you can make a new relativity object using the no argument constructor. Why can you do that? Because if you don't define any constructors in a class, Java automatically makes one for you. Right? The compiler generates the no argument constructor. Right? So in other words, it's as though our class, so it's as though we had the following constructor in the class. Right? A public constructor that's a public no argument constructor that does nothing. Right? So you get this for free. If you don't put one in, if you don't put a constructor in your class. Right? Now the problem is we don't want this to happen. We don't want people to make these relativity objects because there's no purpose and they just take up memory for no reason. Right? So to stop people from making objects of your utility class, just add a constructor to your class. If you make it private, they can't call the constructor. Right? So any private field, constructor, method, or any other feature can only be used inside the class where you declare it. So if we add a private constructor to our class, right, that does nothing because there are no fields to initialize, then no one else can make a relativity object. Inside the class, you can. Right? So if somewhere inside this class, if there was some method or a main method, for example, you could make a relativity object. However, you're probably not going to because you made the class and you know that it's a utility class and you know that the purpose of the class is not to make objects. Right? So adding that private constructor, it doesn't matter what the signature is. Right? You can put in parameters here if you wanted to. As soon as you add a constructor to the class, Java will not insert the no argument one for you. Right, so every time you make a utility class, including on an exam or a quiz, make sure you have a private, empty, no argument constructor that does nothing. Okay, so what else can you have static, what other uses are there for static features in a class? Right, so static features are generally less common than non-static features. Right, normally when you make a class, you're using the class to make objects. If you have objects, you're normally calling methods with those objects. Right? So most of your methods are normally non-static. Most of your fields are normally non-static. However, there is a common use case for static methods, and those things are called static factory methods. So a static factory method is a static method that returns an instance of the class. So in other words, it's a method that returns an object reference. It's called a factory method because inside the method, it makes an object and returns a reference to that object, right? So it's a method that produces objects. The reason this is useful is because you can create a static method that behaves much like a constructor, right? Now remember what a constructor does, right? So when you call a constructor, you use new plus the constructor, right? The combination of new plus the constructor makes an object and initializes the object to some state. A static factory method internally calls a constructor to make an object and then initializes or sets the fields of the object to the desired state. Right? So static factory methods behave like constructors. They create and return a reference to a new object. The important difference is that unlike a constructor, you get to pick the name of the method. And this turns out to be very useful. Right. So remember our point2 class, right? So it's a class that makes objects that have an x and a y coordinate. Right. If you know what the polar form of a point is, then you should know that the polar form of the point you can compute as the polar representation of the point is characterized by the radius or the distance from the origin to the point, and the angle from the x-axis. Right, measured counterclockwise. It's easy to compute the coordinates of that point. It's just r cos theta and r sine theta, right? Where theta is in radians. So the polar form is common in mathematics. So if you decided that you wanted to put in a constructor that lets the user make the polar form of a point, you run into a problem. Right? We have one constructor here that takes in the x and y coordinate of the point. Right. We now want to add a second constructor that takes in the distance to the point from the origin and the angle relative to the x-axis. Right. And notice that the signature of those two constructors are identical. Right. Point 2, double, double, and point 2, double, double. So we are not allowed to put both of these constructors in the class at the same time. Right. It's an illegal overload because they have the same constructor. The same signature. If I wanted to include the polar form constructor, I would have to change either that type, or I'd have to remove one of the parameters, or I'd have to add an extra parameter, right? And none of those options make any sense, right? I really want a second constructor whose signature is point 2 double double. So it looks like I'm stuck, right? But you can fix the problem. You just replace the second constructor with a static factory method. Right. So static factory methods are also called, well, this technique is called the named constructor idiom. Right? So named constructor because the static factory method behaves like a constructor that has a different name. You get to pick the name so you can make it descriptive. Right? So it doesn't have to be the name of the class, in other words. Right? And it behaves exactly like someone had used new and called the constructor. So it's actually very easy to implement the method. You turn your constructor into a static method. So now it's a static method, right, that returns a reference to a point2 object. You give it a name. So in this case, polar makes sense. Polar form would be fine too. Now there's no problem having two parameters of type double and double because there's no other method called polar. Right? And inside the method, all you do is you make a point whose coordinates are r cos theta and r sine theta. Right? And then return a reference to that point. Right? So you compute x and y, and then just make a new point with those x and y coordinates and return a reference to that point. Right? And now you've got a way to you now have a way to make a new point given its polar form. So if you go poking around in the source code for the classes used in this course, right? So if you go and look in point2, or if you look in vector2, which is a companion class to point2, you'll find inside those classes there's a bunch of methods. Right? So there's add, subtract, multiply, divide, and negate. Right? Add lets you add a point and a vector. Subtract lets you subtract 2 points. Multiply lets you multiply a point by a scalar value. Divide lets you divide a point by a scalar value. And negate negates the coordinates of a point. Right? For each one of those methods, there's a matching static factory method. Okay, so the reason why is as follows. So there's a non-static version of add that changes the point used to call the method. So in other words, if you wrote p.addv, that changes p so that its new coordinates are the coordinates of p plus the coordinates of the vector v. Right? So the non-static version mathematically does that. Right? In other words, it changes p. Now there's lots of cases where you don't want to change the point p. Right? So in other words, you want to compute a new point whose coordinates are p plus v, but you don't want to change p. Right? So now what do? Well, you can just add a static version of add. Right? That makes a new point, so it makes q, whose coordinates are p plus v, and it doesn't change p or v. Right? So you get a static version that's equivalent to that equation there, right? And the non-static one is equivalent to that equation there. Inside the Java standard library, these static factory methods are all over the place. Right? So inside all of your wrapper classes, so integer, double, character, blah, 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 right? Inside of them, they all have static factory methods called value of. Right? The integer version takes in an int and returns the integer object equal to that int, or that represents that int. Right? So the double class would have a value of that takes in a double and returns a big D double object, and so on and so on and so forth. In arrays, there's this copy of method. I don't remember if we've used this already or not. Arrays, inside the arrays class, there's a utility method called copy of. It will copy an array for you. And you can specify the length of the new array. Right? So the new array can be longer or shorter than the original array. And it will return a copy of that original, fitting it into the length of the new array. String also has several static factory methods. So format is one of them. Format lets you take in some objects and format them so that they produce a string using the string representation of these objects. Oops, sorry. All right, so there's that ends the lecture on static features. All right, I just have to hunt down the next lecture, sorry. All right, so this part of the lecture is about the method called equals. All right, so if we make a class like point2, or the counter class, or the stopwatch class, right? All of these classes, technically, they extend this class called object, right? So what that means right now, we're not really ready to talk about what that means right now, but you can imagine that our point2 class is also a big O object. A point2 object is also a big O object. Now inside this class object, there's several, I think there's 11 methods. Right? And so what that means is that every class you make also has those 11 methods. One of those methods is equals. Right? And we've seen equals before, right? So in the string class, we've seen that equals lets you compare two strings to see if they represent the same sequence of characters. Right? If you have two lists, equals lets you determine if the two lists contain the same objects in the same order. So if we make a point2 object, P, right, can you call equals using our point2 class? The answer is yes. Right? So this always works. In other words, you can always write x dot equals y for any two references x and y. Right? That's always guaranteed to work, as long as x is not null. Right? So I can write p equals p, and that works just fine. That also returns true in this case. Right? So p is equal to p, which makes sense, right? The 2 points have the same coordinates because, well, it's the same point in this case. So if I make another reference p2, right, and I assign it the reference p, then p2 equals p is also true, right? Also makes sense because p2 and p, they both refer to the same object. If you make a third point whose coordinates are the same as the first, right? So 1, 2, and 1, 2, right? And now if you ask, is p3 equal to p, or is p equal to p3, or is p3 equal to p2, right? You end up with false. Okay, so what's going on in memory is the following. So here's p and p2. Here's p3, right? So the first point lives at address 600. The second point lives at address 700. Right? P and P2, they both refer to that first object there. P3 refers to the second object there. Right? So when you write P dot equals P2, right, the default behavior of equals is to look at these two values here. Right? So is 600 equal to 600? The answer is yes, so you get true. Right? When you write P equals P3 or P3 equals P, right, the default behavior of equals is to look at this value here and that value there. So is 600 equal to 700? The answer is no, and so you get false. Right? So in other words, the implementation of equals that you get from object checks if two references refer to the same object, right? In other words, do they have the same memory address? Right? So x equals y is true if and only if x and y refer to the same object. This behavior is also the same as if you had written x equals y. Right? So when you do equals equals in Java, the behavior is to look at the value here and the value here. Right? If those two values are primitive values, then that's exactly what you want to do. Right? If the two values are reference values, then that may not be what you want to do. Right? So for example, in the point2 class, we probably want to compare, do the 2 points have the same coordinates? Right? So they should support what's called logical equality. Right? Back here, this version of equality is called equality of equality of identity. Do the two references refer to the same object? Right. Here we want logical equality. Right. Do 2 points have the same coordinates? Right. They don't necessarily have to refer to the same object. Right. So in other words, what we want to check for is an instance is equal to another instance if their states are equal. So it turns out in the early days of Java, this was surprisingly hard to do. So I guess in the 90s, when the language was starting to become popular, if you were to pick up a textbook on Java, if you pick up 2 different textbooks on Java, you would probably find 2 different implementations of equals. So this quote is from Angelica Langer. She's a Java consultant. She says that one would expect that overriding equals, since it's fairly common, should be a piece of cake. The reality is far from that. There is an amazing amount of disagreement in the Java community regarding the correct implementation of equals. That's no longer the case. So people have now figured out and decided and agreed on what is the correct way to implement equals. Turns out there's 2 different ways. There's actually a third, but the third is very uncommon. Okay, so we're going to do method number 1 today. Right? So what we're about to do doesn't always do what you're looking for exactly. Right? We'll come back later in the course and look at the well, when are we going to do the second version? I think in the next lecture we do the second version. However, what we're about to do today always satisfies what's called the equals contract. Right? In the online notes, and there used to be a textbook for this course, they would implement equals this way. All right, so this is what we require from equals. Number 1, an object is always equal to itself. That kind of makes sense, right? So x dot equals x is always true. Right. Number 2, x dot equals null is always false. Right? So in other words, an object is never equal to no object. That's part of the contract that you inherit from the object version of equals. Okay, today we're going to say that only objects of the exact same type can be equal. Right? So 2.2 objects can be equal, but a 0.2 object can't be equal to a string. And then finally, the fourth part is logical equality. Right? If the 2 objects have the same state, then they're equal. Okay, so number 1, an instance is always equal to itself, just means that x equals x is always true. Right? Furthermore, x equals y is true if x and y refer to the same object. When you use equals equals with 2 references, you're checking, do the 2 references refer to the same object? Okay, so the other thing you have to remember is that equals always has the exact same signature. Right? Well, it's always the exact same method header. Right? It's always public. It always returns a little b Boolean object. It always returns a little b Boolean value. It's always called equals, and its parameter type is always big O object. Right? If you change any of these, then you're no longer overriding the equals method that you got from object. Right? You're adding a new overloaded method to the class. Right? If you only change the return type or the access modifier, you'll get an error. Okay, so step number 1. An object is always equal to itself. Okay, so how do you call equals? You write something like x dot equals y. Right? Inside the method, right, x is this, right, and y is obj. Right? So if I want to check if x and y are the same object, I can check is this equal to obj. Right? So if they are, then I can return true because they're the same object. You don't actually require this if statement here. Right? So it doesn't technically need to be here, but it's cheap to check. Right? It's just one equality test. Right? So it's very cheap to test, so it's easy to put in. Right? Also, if this happens to be true, you don't have to do the rest of the method, which turns out to be rather expensive to do. Okay, now what about x equals null is always false? Right? So this is also easy to check for. Right? Remember, so inside the method, that thing there is obj. Right? There's another condition regarding null. Right? So if the parameter is null, then equals must never throw an exception. Right? So what do you have to do? Well, it looks like we have to check is obj null. Right? So step 2, If obj is null, return false. So that's how you check if a reference is null, right? Obj equals null. Okay, now this statement has to be here. If this one isn't here, then the next thing we're about to do will fail. It's going to throw a null pointer exception. Right. Step 3. Instances of the same type can be equal. Right. So how do I get, so the question here is, I have to check, is the type of this object the exact same as the type of obj? Right? So is the type of this the same as the type of obj? Right? Whoops, sorry. Okay, so how do I get the type of an object? So it turns out you can't get the exact type of an object. However, you can get something that's close. So inside the object class, there's a method called getClass. Right? It's non-static, right? Which means you can call getClass on any reference. Right? GetClass returns some funny object here. Right? So it returns some object whose type is class, and then it looks like it's some generic type, and there's some funny question mark extends object here. Right? So for the time being, just ignore the question mark extends object. Right? All that we really care about here is that getClass returns an object of type big C class. Right? That object represents the type of the object that you use to call getClass with. So in other words, that's all that you care about right here. Right? So all that we care about is that getClass returns the runtime class of an object. So to compare these two, to compare the class of this object, right, I'm going to use this to call getClass. Right? I want to compare it to the type of obj, so I'm going to use obj to call getClass. Right? And then I'm going to compare them. So it turns out you can use not equals here safely. You could also use equals here safely. Even though getClass returns a reference type. Right? So remember, when you have reference types, you normally use dot equals to compare two types. Here it's okay to use not equals or equals. The reason being is getClass always returns the exact same object for any particular class. Right? So in other words, if you call getClass with a .2 object, it always returns some object of type class, right? And it's always returning the same object every time. Right? It doesn't matter which .2 object you use to call the method with, you always get the same class object that represents the .2 class. Right? So in other words, there's only one class object per type, and the method guarantees that that's always true. Right? So you can safely use equals or not equals here. If they're different, then for today, we're going to return false. Right? So in other words, if this is a .2 object and if obj is a string, those two classes will be different. They can't be equal, so we immediately return false. Okay. So we're now at the point, so if we get past this if statement here, what do we know? Right? We know that this and obj are different objects. Right? We know that obj is not null. And we know that the two objects have the same type. Right? We're now at the point where we want to compare, do the two objects have the same state? Right? So if this is inside the .2 class, I now want to compare the coordinates of this object and the coordinates of obj. Right? But I can't. Right? Because obj is a big O object. Right? So if you go back up here to the signature of the method, right? The type of obj is big O object. Right? And so what does that mean? It means the only thing I can do with obj, right, is to call methods that belong to big O object. Right? Because that's what the method says its type is. Right? Now at this point here, once I get past the if statement, I know that obj is a .2 object. Right? And so I also know that obj has an x and a y coordinate, but I have to convince the compiler that this is true. right? Because as far as the compiler is concerned, obj is a big O object. Right. So here, you need a cast. Right. So the next thing you do is you take obj and you cast it to a point2 object. Right? And you take the result and you store it in a variable called something else. So I always call it other. Right? You have to do this cast because I need to get to the x and y coordinates of other. Right? I can't get to the x and y coordinates of obj because as far as the compiler is concerned, obj is a big O object and not a point2 object. Right? This cast here fails if this if statement is false. Right? So if the two objects have different types, then that cast will fail there. Well, sorry, that's for today. If these two things have different types, this cast will fail. Right? And you'll get an exception of some kind. You'll get a class cast exception. But because I've checked this, because this if statement, we know this if statement is false, right? Then I know that obj really is a point2 object, so this cast is guaranteed to succeed. All right, so I'm now at the point where I can compare the two objects to see if they have the same state. Right? Now when you do this, there's a standard recipe for doing this. Okay, so if your fields that you're comparing, if they have primitive type and they're not floating point, right, then you just compare the fields using equals equals. If your fields happen to be floating point, which they are in this case, then what you're supposed to do is you're supposed to convert your field to an integer type. And the way you do that is you use float to int bits, or big D double to long bits. I'll explain why in a moment. If your field is an array, then you should consider using arrays.equals. If it's a two-dimensional or a three-dimensional or a multi-dimensional array, use arrays.deep equals. Right. And finally, if your fields are some reference type, like a string or a list or something else, just compare them using equals. Okay, so why do we have to go through this nonsense of converting our floating point types to an integer type? Right. So the method float to int bits or double to long bits, right? All they do is they take the float value and convert it to an int value. And the way it does it is it just looks at the bits of the float and reinterprets it as though it were an int. Right? Double to long bits does the same thing. It looks at the bits of the double number and just reinterprets it as though it were a long number. Right? Because float has 32 bits and int has 32 bits. Right? Double has 64 bits, long has 64 bits. All right, so why do we go through this nonsense? Because of the following. Right? So if you take, if your value happens to be not a number, then not a number equals not a number is always false, which looks strange, but that's the way that the IEEE 754 standard says it has to behave. Right? So nan is never equal to nan is equal to nothing, not even itself. Right? And that's inconvenient. Right? Because if you're comparing two objects and you want to know if their states are the same, right? If one of their fields is not a number, sorry, if both of their fields are not a number, then you probably want them to be equals. Right? But if you just compared them using equals equals, you run into this problem here. Right? Now, when you convert them to their long representation, though, equals equals returns true. Right? Because not a number has, if both numbers are not a number, right, they both have the same long representation. There's another reason why you should do this. If you have two primitive values, then -0 equals +0 is true. Right? But if you look at their actual binary representation, -0 and +0 are different. Right? So in other words, they're not the same. Right? So if you run -0 through double to the long bits, and compare it to running 0 through double the long bits, you get false, right? And so this is the behavior, these two things here are the behavior you want to capture because that's the way the rest of the standard library works, right? So in other words, if you just compare two double values using equals equals, right, then your class behaves differently than any other standard library class. Right? And we want them to behave the same as the standard library classes. So you have to go through this somewhat convoluted exercise. Right? So I'm going to check, is the x coordinate of this point and the x coordinate of the other point, are they not the same? Right? If they're different, then I can return false. Right? If they are the same, then I have to compare the x coordinate of this point and the y coordinate of this point. If they're not the same, I can return false. Right? Now I finally compared the coordinates of the 2 points. If they're both the same, I can finally return true. Right? So our version of equals compares the state of 2 points to determine equality. 2 points with the same coordinates are now considered equals. Right? So if we take this equals method, insert it into our point2 class, right, then when we do something like this, so P is the point -1, 1.5. Right? Q is a copy of P. It's created using the copy constructor. Right? So in other words, it has the exact same coordinates, -1 and 1.5. Then when you ask, are they equals? You get true. Okay, so the equals contract. So this is part. When you actually look at the documentation for equals inside the object class, what you'll encounter is a very mathematical specification of the method. Right? So when you read the documentation, you'll see that it says equals must be these 5 things. Right? It has to be reflexive, symmetric, transitive, consistent, and it must not throw an exception when passed null. Right? Now fortunately, these 5 things, they just mean what we described earlier in the lecture. So reflexivity, that's just the fancy mathematical way of saying that an object is always equal to itself. Right? So x equals x is always true. Symmetry just means that if you flip the order of the 2 arguments, then you get the same result as long as that one's not null. Right? So in plain English, 2 objects must agree on whether or not they're equal. Right? If x equals y is true, then y equals x must also be true. Right? If x equals y is false and y is not null, then y equals x is also false. Transitivity just means that if you chain if you have 3 objects and you compare them, the first 2 and the second 2, then they have to agree on whether or not they're equal. Right? So if x equals y is true and y equals z is true, then it must also be the case that x and z are equal. Right? Because x and y have agreed they're equal, y and z have agreed they're equal. That means x and z must also be equal. Consistency just means that equals shouldn't be random. Right? So if you compare 2 objects and their state never changes, then equals always returns the same value. And finally, x equals null is always false and never throws an exception. Right? So that's the 5th part of the equals contract. Right? So those 5 things there, if you ever see the term equals contract, that's what people are referring to. Okay. When you implement equals, it's always the exact same steps. Right? So if you're going to implement counter version of equals, right, then you do all of the same things all over again. Right? So inside the counter class, step 1, check is this equal to obj. Step 2, check if obj is null. Step 3, check are the 2 classes different. Right? Step 4, perform your cast. Right? Step 5, compare the fields of your objects. Right? Using the recipe that I showed you 10 slides ago or so. Right? Now, before you go, so on a quiz, you have to remember, or on the exam, you have to remember the steps of implementing equals. In practice, though, right, when you're inside any decent IDE, right, you can go into a class. Let me see if I can find a class. Sorry. So I'm just going to open up, sorry. I'm just going to open up the point class. Let me just check if equals is already here. Okay, so let me delete equals. Okay, so in practice, though, your IDE will generate equals and a companion method for you. Right? So in Eclipse, inside your class, you can go to the source menu. Source, and then down here you will see generate hash code and equals. Right? Click on that. The wizard will ask you, what fields do you want to compare for equals? So I want to compare the x and y coordinates of the 2 points. Right. Use it. Okay, so that's good. So down here you have some options, right? For now, I'm just going to use the last. Well, you don't even need to use the last one. I'll just click generate for now, and Eclipse automatically generates equals for you, right? And it does exactly the steps that we just did, right? Checks if this is equal to OBJ. Checks if OBJ is null. Checks if the two objects have different types, performs the cast, right? And then uses double the long bits to compare the two fields, right? And away you go. Yeah?
So the 5 equal rows you just taught us, is that the same for the next way we discover equals next lecture?
No, this step here changes. That one right there. So there is a difference. Although we won't really be able to appreciate the difference until we talk about inheritance. But there is another way, yeah. Any other questions? All right, so that's it for today. See you, I guess, when? No, today's Tuesday, Thursday.